In our last lesson, we talked a little bit about the difference between definitions, postulates, and theorems, and today we're going to explore postulates a little bit more. So, just to remind you, if you are using a definition, well, defines what an object is. So, if I'm saying that an object is a bird that is about, I don't know, this size, and it has a very colorful tail, then you may make an assumption that I'm talking about a rooster, right? It's a bird, it has a colorful tail. Maybe I will add some other specifics, and that is a definition. A postulate is something common that makes common sense. It doesn't require a proof. We know that it's true. And the theorem is some other logical statement, but it might make you go, and that might require some proof. So a theorem is a logical statement that requires proof, and postulate does not require a proof. You will see today in the lesson some examples, and then you will understand it will be much more clear what's the difference between those. So for starters, in the notebooks, we are going to start a table like I have here on the screen. You will have a postulate, you'll have examples and diagrams. For some of them, we might skip one or another, but that's the basic setup for our postulates. And we're going to start with a point, line, and plane postulate. We first talked about points, lines, and planes, so that's going to be our very first postulate. And we will start with the unique line assumption, which says that through any 2 points, there is exactly one line. If I'm drawing a point and another point, there is only one line I can draw through those 2 points. I cannot move it like any other way, so that it goes like any other line goes through those 2 points. There is only one line that can go through those points A and B. There is, well, that's a diagram, which is an example, right? We can draw line AB through those 2 points A and B. Now, the second part is a number line assumption. So I'm going to be using the space here on the right for the diagram. Every line is a set of points that can be put into one-to-one correspondence with the real numbers, with any point on it corresponding to 0 and any other point corresponding to 1. So I'm going to start my line like this. That's going to be my number line. Since it's a number line, I will put the arrows at the ends. And look at this. It says that any point on the line can correspond to 0. So I can pick a 0 being over here, over here, over here. It doesn't matter. We usually pick a 0 that works out the best with our example. If there is no specific example, we usually pick a 0 somewhere in the middle. But I might want to pick a 0 that is on this kind of like bold line. So I will say this is a 0. And then I will pick any other point that corresponds to 1. And when we have our graph notebooks, it's common to choose one box as a 1, but it doesn't have to be. I might say that this is 1. So 3 little boxes is 1. Those are my choices. You have a freedom in choosing whatever you want for 0, whatever you want for 1. Everything else will depend on those choices, on those 2 choices. So now it says that all points and all numbers are put into one-to-one correspondence. What that means is that for any single point on a line, like if I choose this point over here, I can figure it out a number. So I can say that, oh, it's the same distance as from 0 to 1, so it has to be -1. Vice versa, if I think of a number, I can always find the point for it. So let's say I'm thinking of a number -3. Then I will say, oh, okay, so -3 has to be right here. I will find that number on a number line. And it doesn't have to be whole numbers. I can say of negative, I don't know, 1.5, right? So negative 1.5 is going to be right there. So I thought of a number, I found the point that corresponds to that number. This is what the number line assumption says. Okay, so every line is a set of points. So line is kind of like made up of points that can be put into a one-to-one correspondence with the real numbers. So if I think of a number, I can find the point. If I think of a point. If I see a point, I can find the corresponding number to that point. That's what one-to-one correspondence means. And we have a choice, we have a freedom in choosing any number that corresponds to 0 and any number that corresponds to 1. That is our second part. Next part is dimension assumption. So if you have a line in the plane, there is one point, at least one point in the plane that is not on the line. So I have a line, and I can choose at least, or I can find at least one point that is not on this line. Here we go. There is point A that is not on line L. And given a plane in a space, there is at least one point in space that is not in line. So let's see if I can draw. No, that doesn't give me, that does not give me a parallelogram. So I'm just going to draw it by hand. So we usually draw, when we draw a plane, we usually draw a parallelogram. So I have my plane M. So I can find at least one point in space that is not on the plane. So if I draw a point over here, it is in the plane. And if I draw a point, let's say over here, then that point, point B, is not in plane M. So B is not in plane M. A is not on line L. Remember, we can label our lines with either two capital letters with the little two-sided arrow on top, or with one lowercase letter and there is nothing on top of that. Next theorem is a line intersection theorem. So this one is a theorem. It says that we have two different lines. They can intersect in at most one point. So if I have, so the simplest example, I have these two lines. They intersect in at most one point. Or I can have two lines that go like this, right? They're different lines. And then you can see they do not intersect. So my line L and line M, they intersect in one point. Point A, L, and M intersect at point A. And then I have line N and I have line K, N and K. They don't intersect. So you can see that this theorem, it's not talking about the plane. It's not necessarily two lines in one plane. I was drawing the lines that are in one plane, but they can be other lines that are not necessarily in one plane. So look at this. If I have a line going like this, and then I have another line going like this, from your perspective, it looks like they intersect. But if I turn my diagram this way, see, they don't intersect. If they were intersecting, they would be touching each other, but they don't. So these two lines, they don't intersect. They are in different planes in space. And you can see that this line intersection theorem still holds because it's two different lines and they intersect in at most one point, which means that maybe they intersect or maybe they don't. They cannot intersect in 2 points, right? If I have something like this, well, this one is not a line anymore, it's a curve. By the way, when we say straight line, that's kind of like overdoing it because lines are always straight. Now, that brings us to a definition of parallel lines. We would say now that two coplanar lines, we remember what coplanar means. That means those two lines are in the same plane. Two coplanar lines, M and N, are parallel, written M parallel to N, so M parallel to N, if and only if they have no points in common or they are identical. So when we think about parallel lines, we usually think about something that looks like this. The notation for it is we put little set of arrows on those lines. So if you have an additional arrow here, that means that they're parallel. So those two lines are parallel, or they can be identical. So for example, if I use another line that that is not what I wanted a line. So if I use another line that goes like this, right, it goes right on top of N, so it is identical to N, And I can say that my red line and the line N, so red line, line L, and then the green line, line N, they are parallel. So I can say that L is parallel to N. This is kind of like not used very often because it kind of like, okay, whatever, it's the same line. Why would we say that it's parallel? But we can say that the line is parallel to itself. So sometimes you might see it. That's why I thought I would tell you about this. And that's a definition of parallel lines. Now on to the distance postulate. The distance postulate has three parts. One is uniqueness property, then distance formula, slightly different from what we did in class before, and additive property, not addictive, additive property. Uniqueness property. On a line, there is a unique distance between 2 points. So same thing, we have a line. Remember we said that we can make it into a number line, but if I want to measure the distance from here to here, right? If I want to measure this distance from my point A to my point B, then there is only one number that I'm going to get. So I will say that N equals AB. Remember, AB without anything on top means it's the distance between A and B. If I measure, I can put my ruler so that it goes from A to B or it goes from B to A, it will still give me one number. There is a unique distance between 2 points. Now, for the distance formula, we would use the line and then we would use, so it's not the coordinate plane, it's just a line. So I have 2 points and I have the coordinates of those two numbers, X and Y. And I don't know where 0 is. It might be between, it might be to the right, to the left, we don't know. So we have 2 points here. So then we would say that the distance AB is going to be the absolute value of X minus Y. Okay, why do we have to put the absolute value? Because distance is always positive. Imagine that X was 3 and Y was equal 5. If I do 3 minus 5, I'm going to get negative 2. But if I put the absolute value around 3 minus 5, then I'm going to get 2, and 2 is a positive value. That means that the distance is going to be equal to. If I have, let's say, negative 3 minus 5, then this equation still works. Negative 3 minus negative 5. We put the absolute value. It's the same thing as saying negative 3 plus 5, which is going to be equal positive 2. So still our distance equals 2. And then my last example is, let's say this is negative 3, and then this guy is positive 5. So I will do negative 3 minus 5, right? Minus positive 5. And then if I didn't have an absolute value, I would end up with negative 8. But with absolute value, the distance is going to be 8. So those are my examples here. And then the final part is additive property. If we have a segment AC now, so look at this, we have a segment, it's not a line anymore, so that means the end points are called A and C, and I have a point B somewhere between those. B is on segment AC, doesn't have to be in the middle. It's always very tempting to say, oh, B is in the middle. No, what that tells us is that if I add AB, this distance, plus BC, then I'm going to get the whole distance, right? So I can just say here AB plus BC equals AC, kind of repeating what I said here. And that, again, that is a common sense, right? If this distance is 1 and this distance is 5, then the whole distance has to be equal 6, 1 plus 5. We can use it kind of like backwards. So if I, for example, if I know this is 5 and this is 6, then I can say, oh, 6 minus 5, this little piece has to be equal 1. Okay, so those are our postulates for today, and I hope you enjoyed this video. Give me a thumbs up or like or whatever you do with YouTube, and I'll see you in class.